You ever just look up at the sky and wonder if there's some kind of master blueprint for the universe? A single, simple set of rules that controls everything from a falling apple to the incredible dance of the planets. Well, what if I told you we've had the key to that blueprint for centuries? An engine, not made of metal and gears, but of pure logic. An algorithm that can literally compute the future.
You know, before Isaac Newton came along, the cosmos was just a total mystery. Planets seemed to just wander around up there in ways that felt completely random and unknowable. And then Newton gave us this engine, and suddenly the universe transformed into this beautiful, intricate, understandable clockwork. For the very first time, the future was something we could actually calculate. So the big question is, how did we crack this cosmic code?
Okay, so to get a handle on this engine, we've got to learn its language first. See, in physics, words have these super precise meanings, and sometimes they're not at all what our everyday intuition tells us.
Yeah, our common sense can really lead us astray here. For instance, we all use mass and weight like they're the same thing, right? But they're not, at all. Mass is how much stuff is in an object. It's resistance to being pushed. Weight is just the local force of gravity pulling on that mass. So you on Mars, you'd have the exact same mass, it's just as hard to get you moving, but you'd weigh a whole lot less. Same idea with speed and velocity. Speed is just a number, 60 miles an hour. But velocity has direction. 60 miles an hour north is a completely different velocity than 60 miles an hour east, and getting that distinction right is absolutely crucial for our engine to work.
All right, now that we've got our vocabulary straight, we can finally look at the blueprint for this universal engine. And it all comes down to one single, beautiful rule that describes all change in motion: Newton's second law.
Now, the key here is not to just see F equals ma as some formula you memorize for a test. It's really a story about cause and effect. Think of it this way. Force, the F, that's your input. That's the actual push or pull. Mass, the M, is the resistance, the object's built-in laziness, you could say. And acceleration, the A, that's the output. It's the exact change in velocity you get when that force acts on that mass.
And we have to be super clear about acceleration, because this trips people up. It's not just slamming on the gas pedal. Remember how velocity includes direction? Well, that means any change in direction is also an acceleration. If you're driving your car around a corner, even at a perfectly steady speed, you are accelerating. And if you're accelerating, our blueprint tells us there has to be a force making it happen. In this case, it's the friction from your tires gripping the road and pushing the car into that curve.
So how does this one little rule build into something so incredibly powerful? We've got the blueprint, F equals ma. Now let's see how we actually use it to build a predictive engine that can step forward through time.
This is the real million-dollar question, isn't it? How do we take this one static rule and turn it into a machine that tells us where something is going to be, not just right now, but in the next second, and the next, and the next?
Well, the answer is a surprisingly simple little loop. A recipe, really. It works like this. Step 1, you have to know where your object is right now. That's its position. Step 2, based on that position, you figure out all the forces acting on it, like gravity or the pull of a spring. Step 3, you use our blueprint, F equals ma, to find the exact acceleration those forces are causing. Step 4, that acceleration tells you exactly how to update the object's velocity for the next tiny moment in time. And finally, Step 5, that brand new velocity tells you the object's new position. And then, you just start the loop all over again from that new position.
And here it is, the whole process visualized as this perfect self-contained engine. You see how it flows. Position tells you the force tells you the acceleration updates the velocity, and the velocity gives you the next position. It's this incredible cycle. If you know everything about an object right now, this engine can compute everything about it an instant from now. And by just repeating that loop over and over and over, you can chart out its entire future, one tiny little step at a time. Okay, this all sounds amazing in theory, super powerful. But does it actually work in the real world? Let's put this engine to the test. We're going to try it on two completely different systems just to see if it holds up.
So for our first test, we've got a classic, a mass on a spring. We're going to pull that mass out to a position of exactly 1 and then just let it go. Now, the force law for this setup is really simple. The spring pulls back harder the farther you stretch it. That's it. That's the only rule our engine needs to know.
And now, we run the engine. We start at time 0. Position is 1, velocity is 0. Based on that position, our spring rule tells us the acceleration is -1. We use that to calculate a new velocity and a new position just 1/10 of a second later. Then we do it again. We take those new values and repeat the whole process. Step by step, we're building the future with just simple arithmetic.
And here it is. This is the aha moment. When we take all those individual calculated points and plot them on a graph, something incredible emerges. That simple step-by-step math perfectly creates the smooth, beautiful wave of the spring's motion. We started with just one simple rule, and we ended up with a perfect prediction. The engine works.
So, the engine passed the first test. But okay, it's a spring. Big deal, right? Well, here's where it gets mind-blowing. We can use the exact same engine, the very same computational loop, to calculate the orbit of a planet. The only thing we have to do is swap out the rule for the spring with the rule for gravity.
Test number 2, a planet orbiting the sun. We give it a starting position and a starting velocity to get it going. Now, the force law is Newton's law of gravity, which depends on where the planet is in space. The engine's job is to take that position, calculate the force of gravity, figure out the acceleration, and update the velocity. Same loop, different rule. And just look at that result. Each one of those dots is one spin of our engine's calculation. And together, what did they trace out? A perfect ellipse. You can even see the physics happening right there. The dots are spread farther apart when the planet is close to the sun, because it's moving faster, and they're bunched up when it's far away and moving slower. Our simple little engine just derived Kepler's laws of planetary motion, all on its own. It's incredible.
So, we've proved it. The engine works for one spring, and it works for one planet. But its real power, its true power, is how it can scale up to handle almost unimaginable complexity. Let's look out to the horizon.
Think about what's called the n-body problem, trying to calculate the motion of every planet in the solar system at once. The force on Jupiter, for example, isn't just from the sun. It's getting these tiny gravitational tugs from Saturn, from Earth, from Mars, from every single other body out there. The algorithm, the loop, is exactly the same, but that one calculate the force step becomes gigantic.
Trying to do this by hand? Forget it. It would take a lifetime. But a computer can run our engine's loop millions of times a second. It can also make the time step between calculations incredibly small, and that's the key, because the error gets smaller with the square of the time step. If you make the step 1,000 times smaller, your result becomes 1,000,000 times more accurate.
So, how fast are we talking? Well, a modern computer can run our engine to calculate Jupiter's entire 12-year orbit, including all the tiny pulls from every other planet in the solar system, to an accuracy of 1 part in a billion in about 2 minutes. And this all leads to the most profound insight of all. It's all the same engine. Nature, it seems, runs on a single blueprint, whether it's an apple falling from a tree, a spring bouncing up and down, or the grand, majestic clockwork of an entire solar system. The universe is computing its own future, step by step, using this exact same code. The scale doesn't matter. The loop is absolute.
Before Newton, all we could do was watch the sky and wonder. But now, armed with this engine and the rules to feed it, we can actually predict what's going to happen. And that is a profound shift. Understanding the precise rules of right now means you can master the future.
Which leaves us with one final huge thought. This engine has proven itself to be universal for physical motion. But if the universe really does operate on a set of rules that can be computed, what else can this engine predict?